Hello and welcome to this PIR live event webinar brought to you by Partners in Research Canada. My name is Stacey Joyce and I will be your host today. If you're joining us live, please remember that you can ask questions anytime throughout the webinar by clicking chat in the top left corner of your screen, changing the to field to include attendees so everyone can see what it is that you're asking, and then type in your question to us. If it's not time for questions yet, we'll queue it up to ask it when it is time. And let us know where that question's coming from, if you would. So whether that's a school name or your city, maybe even a student first name or a grade level, so that we can give you a shout out when we ask your question. So today's guest is Dr. Gordon Osinski. He's also known as Oz, or Dr. Oz. He's the director at the Center for Planetary Science and Exploration and an associate professor in the departments of Earth Sciences and Physics and Astronomy, all at Western University in London, Ontario. Thank you so much for joining us, Dr. Oz. I will let you take it away.
Okay, it's a pleasure to be here, and I'll start by sharing my screen. Okay, so hopefully you can all see the screen now. And I was asked to talk today about a major topic of my research, which is meteorite impacts, and we'll talk about matters of life and death. And so again, we'll have lots of time for questions at the end, but if you have a burning question as we go through this, don't kind of hesitate to put up your virtual hand, and Stacey can let me know. So perhaps I'll actually start with a question for all of you out there, which is to get you to think about what's the first thing that pops into your head when I say the word meteorite impacts. So maybe it's something like this. This, of course, is a really giant asteroid that is striking the Earth. This is obviously an artist's rendition. And as we'll go into a little later on, thankfully for us humans and other life forms on Earth, these large meteorite impacts are very uncommon, happening maybe every few million years throughout time. But bearing in mind the Earth is about 4,500 million years old, these kinds of things occur very frequently to myself as a geologist throughout time. But perhaps you might be surprised to know that something on the order of 50 to 100 tons of material strikes the surface of the Earth every day from space. So, well, why don't we know about that? We do to a certain extent. Hopefully everybody out there has had the kind of the really great experience of seeing a shooting star. So on a clear night, and whenever you look up and see a shooting star, what you're looking at is material that is maybe a few grams or kilograms in size that is basically burning up as it comes through the Earth's atmosphere. So this is material that is not big enough to hit the ground and strike the surface to form what we call a meteorite impact crater. But if we look at the Earth and our kind of two closest solar system neighbors, hopefully you can see some kind of major differences between these objects. Of course, in the top left, we have the Moon. Even on a clear night without the aid of a telescope, although a telescope, even a very simple one, definitely helps. And you can see that the Moon is pockmarked by literally hundreds and thousands of meteorite impact craters. So if you can see my cursor, it's a little small. All of these circular features are giant impact craters, small impact craters. Some of the biggest ones in the solar system are over 2,000 kilometers in diameter, which we know would kind of swallow up a giant part of Canada. Those all occur on the Moon. Mars is a big planetary object in the solar system. It's of a lot of interest in the search for life. It's a planet that I study too. Mars is kind of in between the Earth and the Moon. In the kind of lower hemisphere, in these darker terrains, you'll be kind of hard pushed at times to find impact craters. But once your eyes get tuned into kind of the red planet, the orange color, you'll hopefully also see lots and lots of circular features that are all meteorite impact craters. Of course, when you look at Earth, and particularly this view, I'll challenge anyone to find an impact crater in this view. But if we go to a slightly different view of the Earth, this is kind of a simple map with the Earth folded out. And all of these red dots are confirmed meteorite impacts. And we know now of about 190 or so on Earth. And we can come back to this at the end. You will notice that they're not randomly distributed across the Earth. There's a lot here in North America, in Scandinavia, and in Australia. few in South Africa, but then there's kind of large expanses of the Earth and most of the ocean basins where we haven't yet discovered meteorite impact craters. Of course, if you do look at Canada, you'll see that we have quite a large number. About 30 or so of the 190 meteorite impact craters that we've discovered are found here in Canada. And there's 3 pictures of some quite famous ones on the right-hand side there. The one in the top right is up in northern Quebec. That's about 4 kilometers across. So it's what we call a simple crater, big hole in the ground, about 4 kilometers across, all the way down to the bottom right, which is an image you might be familiar with if you're listening from Quebec. This is the Manicouagan Reservoir, and that crater there is about 100 kilometers across. And the feature you see in the bottom left of that image is actually a part of the space shuttle. So this is one of the few craters that you can actually see from space. So I think probably what most of you, most people think about when we think of meteorite impacts is the destructive power of impacts. There's been movies such as Deep Impact in kind of the late 90s, quite a long time ago now. And I do not want to even begin trying to understand this plot in this graph, but basically what it is trying to show is on the y-axis, on the vertical axis, is how frequently impact events occur. And on the x-axis, so the horizontal, is how explosive or how destructive these events are. And so kind of 10 to the 2 is something that happens every 100 years or so. And this is trying to equate it to other kind of phenomena that happens on Earth. And so you'll see that even something like Meteor Crater, which is a relatively small impact crater on Earth, it's down there in Arizona near the Grand Canyon. Fantastic place if you get to go and visit sometime. Meteor Crater happens every maybe a few thousand years, and it's more destructive than any of the world's kind of nuclear weapons. And so just to put that in perspective. And then as we go kind of up inside to something like the Chicxulub crater in Mexico, it is almost 200 kilometers in diameter. So just kind of pause and think about that for a second. Here in where I'm sat in London, Ontario, that would be a hole in the ground between here and Windsor, essentially. And then there'd be lots of material spread around. Thankfully, those big events only happen every 100 million years or so, but the energies involved is in the millions of tons of TNT equivalent. And that kind of leads on to this. So maybe this is something else you thought about when you first thought about meteorite impacts. Of course, that Chicxulub crater, as it's known in Mexico, has been blamed for the extinction of the dinosaurs about 66 million years ago. Not just the dinosaurs, but about 50% of all species, all living things on Earth perished right at that very small moment in geological time. And the idea is that you had, not as is shown on this image, but one large asteroid hurtled down to what is now Mexico. This asteroid was maybe 10 or 20 kilometers across, and it made this giant impact crater. So scientists are still figuring out exactly why all of these species went extinct. It's one of the kind of outstanding problems that a lot of us are actually working on now, because for a mass extinction, you've got to really have global consequences. Of course, right at the point of impact, it's kind of game over. It's ground zero, you'd have a blast wave, fireball, and that would basically kill off anything in the few hundred kilometers. But more globally, the idea is that this impact probably threw up enough material into the atmosphere to block out the sun, to cool the temperatures, and basically change the climate of the Earth globally. And if you block out the sun, you eventually kill off the plants, and the plant-eating animals will eventually die off, and then things like T-Rex pictured here would have eventually kind of perished. But again, there's lots of questions that we're still trying to figure out in terms of this impact event. So let's kind of on the negative side now, and this is maybe one of the surprising things, and is a lot of what my research has focused on in the last few years, is actually what I would call the beneficial effects of meteorite impacts. So this was an article I wrote a long time ago for New Scientist. I didn't get to see the title before they put this magazine out, so I'm not sure I totally agree with the cradle of life, but what I'll hopefully kind of finish up with today is showing you that after impacts form, after that initial very short-lived destructive phase, they can actually be beneficial for life, maybe important for the origin of life on Earth, billions of years ago, and maybe Mars as we go out there in the solar system. So what I'm going to talk about is not everything on this screen, but I'm going to talk about habitats. So basically, habitats, environments where that impact craters form that were not there before the impact that life could then colonize. And when I'm thinking life here, I'm really thinking and talking about microscopic life. And one of the big things, and in fact, the only thing I'll have time to talk about today, is what we call hydrothermal systems. So what do I mean by a hydrothermal system? Well, it actually comes from two Greek words, hydros and thermos, basically heat and water. You put the two together and you generate what we call a hydrothermal system. So you may be more familiar with the term hot springs. So if you've been to Iceland, New Zealand, this picture here is Yellowstone in Wyoming, or perhaps even in places in the Rockies in Alberta and British Columbia, you can see natural hot springs. So these are where you have hot liquids rising up through the Earth's crust, and they're heated by hot rocks down at depth, usually from volcanic heat sources, magma chambers. But then it just turns out, because of the energies deposited on the Earth because of impact craters, that can also generate hydrothermal systems. Why are hydrothermal systems important? Well, if you might look at this image and maybe look at the trees in the background, but what I'm more interested in, and what most of the scientists who study hydrothermal systems are interested in, is all of this kind of orange, you might call it gunk. All of this scummy looking material in the foreground, this orange material is life. It's primitive life, it's cyanobacteria, but it's thriving at temperatures well over 100 degrees Celsius, so well over the boiling point of water. And so again, it turns out, and a lot of my research has been working on these systems for the last few years, and so I'm just going to take you kind of briefly now, show you some of the evidence, and then we'll kind of stop and take questions. So one of the structures that, of course, this is Canada. This is all the impact craters that we know of in Canada. And I've been working on this little red dot way up in the Canadian Arctic called the Horton impact crater for the last almost 2 decades now. So this is a satellite image of the impact crater, and it's about 23 kilometers across. And the green material in the middle is not snow, although if you look into the top right of this image, you can see some ice-covered lakes. So this is a very barren environment. This is kind of zooming in closer. It's in what we call a polar desert environment, and that means it's absolutely great for doing geology. Unlike here in southern Ontario, there's no vegetation, no plants, basically not much of anything to get in the way of the rocks that myself as a geologist are interested in. And so kind of combining about 10, 15 years of work into one slide, we see lots of evidence for this hydrothermal activity. So the liquids, the hot springs are not there at the present day. So what we're looking at is kind of fossil or old evidence for these hot springs. So there's 2 pictures here. There's a rock hammer for scale. It's about kind of yay big, about 30 or 40 centimeters long. The greenish material in the upper image on the left is actually iron sulfide. You may know it by its name, kind of fool's gold. In the bottom right, you often see this material in gem and mineral shows. This is a transparent version of gypsum, which is a salt called selenite. And in this case, the crystals are very, very big. And so as we piece together where these deposits are found throughout this crater in the Canadian Arctic, we've come up with this idea that they were important and for life and created a hydrothermal system. So just kind of in wrapping up, and to kind of close the story here, this idea of hydrothermal environments being places where life on Earth originated is not new. It really took hold in the 1960s and 70s, but actually even Charles Darwin, in his famous book from well over 100 years ago, talked a bit about this idea of a warm little pond where all the ingredients for life were found. So all of these present-day hot springs in those photographs on the right-hand side are again in very volcanically active regions on Earth. But over the past kind of decade, at the Horton crater and others throughout Canada and the world, we've really pieced together the evidence that impacts, meteorite impacts, can also create these hydrothermal systems. and because of that, potentially provided environments for life. And so why hydrothermal systems has been important for life? Well, again, this is a very complex but simple diagram on the left. This is our terrestrial, the tree of life. So all life on Earth is on that screen in what we call the tree of life. And the important thing I want to draw your attention to is that it's color-coded for temperature. So just like any kind of actual tree, the oldest forms of life on Earth we know about are right at the place where these three branches meet. And they're color-coded red because they're what we call thermophilic, heat-loving organisms. And so because of this, we think that life on Earth originated in these so-called hydrothermal systems. And we therefore think life on Mars, potentially, if it did exist, would have also arisen in these same hydrothermal environments. And what we can say based on the research we've been doing at Western and elsewhere again is that not just volcanoes create these hydrothermal systems, but also meteorite impacts. So basically kind of wrapping it up, the title of this talk kind of hopefully summarizes the fact that yes, meteorite impacts can be very destructive. And of course, if one happened today, it would be very destructive for life on Earth. But after that fact, they can actually be beneficial for life. It may have even been a place where life on Earth originated. And I think I saw a bunch of hands going up there, and so I'll happily stop here and take questions.
Wonderful, thank you. Before you take that slide, I lost it there. I was just going to ask where that image was taken on your last slide.
Right back. So this is actually one of my other favorite locations working out in the Canadian Arctic. This is a Tunnunik impact crater that's on Victoria Island in the Northwest Territories and not Nunavut. So yeah, a lot of my research has taken place up in the very kind of high northern parts of Canada.
Wonderful. Well, thank you very much for putting that slide back up. We have numerous questions already coming in, but if you haven't sent yours in yet, please do. We do have lots of time for questions today. First question coming from the grade 5-6 class at Lawfield. They're wondering what country has the most meteor impacts?
Oh, that's a really great question, actually. That's a question I've never been asked before, but I probably should know the answer. If I had to guess, I would actually say Canada. Australia's probably a close second. And then if you looked at that map, there's a big concentration in Scandinavia, but that comprises Finland, Sweden, and Norway. So I think I will be right in saying that it's Canada, but I should probably go away and double check that. Yeah, great question.
Wonderful. Next question is coming from Ms. Shepard's class, wondering what is the biggest meteorite that has hit the Earth?
Another great question. So ones that are confirmed, basically the two biggest impact structures on Earth we know about. The second biggest is actually not too far away from here. And I don't know where everybody is online, but Sudbury, that many of you may know about, is actually the site of what we estimate was about a 200-kilometer diameter crater that was formed a long, long time ago, almost 2 billion years ago. The record holder that we know about on Earth is actually a place called Vredefort in South Africa, and that crater is estimated to be about 300 kilometers across. But the problem with Earth is that it's actually very geologically active, and so I mentioned right at the beginning there was craters on the moon that is like 2,000 kilometers across. Those craters of that size probably also happened on Earth kind of 4 billion years ago, but they've all been lost through to erosion. So Vredefort, currently South Africa, is number one, and Sudbury is a close second at number 2.
Right. And we have a question here about how many meteorites have hit the Earth in total. So you just described why we likely don't know the answer because some of the evidence may be gone. Yeah. Are there any other challenges that make that question difficult to answer?
Yeah, I mean, it's almost impossible to answer. And I'll maybe just kind of clarify a little bit too, because when, strictly speaking, when we talk about meteorites, that is the material that survives the passage through the atmosphere, and there are actually things we can walk around and pick up. And one of the things about meteorite impact craters is that usually, because the energies are so high, the meteorite itself gets vaporized or melted and is lost. So we typically only find meteorites that basically those big shooting stars where the material slows down enough but doesn't burn up completely, and that can fall to the surface. And we know from going to places like Antarctica and the deserts of Africa that there are literally we're well over probably 50 or so thousand meteorites now that have been found globally. But again, these are these small, few kilogram size pieces. Back in time, there must have been, tens of thousands of meteorite impact craters that have formed on Earth. But as I kind of mentioned, in the answer to the last question, most of those have been eroded, covered by volcanism, or lost through what we call plate tectonics.
Right. And so talking about the idea that this meteorite falls through the sky, we see this as a shooting star, and if it has enough mass, it makes it through the atmosphere. One of our viewers today, John, is wondering, what would a meteorite be worth if you found one? And perhaps what should our viewers do if they find one?
Well, we can start with the last question. If you ever do think you found a meteorite, we do have a kind of link on our website here at Western and the Center for Planetary Science and Exploration, and we go through a bit of a how to perhaps do a bit of your own homework before contacting us. Really fresh ones, because they pass through the atmosphere and become a fireball, they have what we call a fusion crust, and it's a very kind of glassy, shiny outer surface, and so that's the first telltale sign. And if you went online and went into Google, you'll find lots of information about how to recognize a meteorite. In terms of what they're worth, it's a huge range. Some meteorites are worth almost nothing because they're so common. Finding meteorites is very rare in Canada, but in North Africa and the deserts, again, people have found tens of thousands of these. So you can often find meteorites for sale at gem and mineral shows. So there are very rare ones, though. The rarest, or some of the rarest would be those from like the Moon and Mars, for example. And some of those can go for, hundreds of dollars a gram, potentially. So, if you find a good fist-sized piece, you could definitely sell that for quite a bit of money.
Right.
I'd say those are the exception. Yeah.
Right. So you never know, then. It's possible.
Yeah. No.
Okay, we also have a question here from Caroline wondering, are there elements in asteroids or meteors that you can't find on Earth?
Fantastic question. Another one. So there are no elements that we've yet found that you cannot find anywhere on Earth, but there are lots of elements that are very rare, incredibly rare on the surface of the Earth. And in fact, this is how we sometimes use some of the indicators that we use to prove something as either a meteorite or an asteroid or not. And historically, how that Chicxulub impact crater in Mexico was found was one particular element that you might be familiar with, which is iridium. So iridium is very uncommon on the surface of the Earth, but it is quite common in many meteorite types. And so what they found was actually a spike in iridium at this moment in geological time that they eventually used to piece together evidence to find eventually, about 10 years later, this impact crater in Mexico.
Very interesting. I want to get to a question now from the grade 4s at Forest Manor Public School. And they're wondering if meteorites happen daily. So I want to separate this question into two pieces, because we did touch briefly on a meteorite or a meteor versus a meteorite versus an impact event.
Yeah.
Can you maybe clarify the difference between those and which might happen daily?
Sure. So yeah, a meteor is what we term, that bit of rock as it's passing through the Earth's atmosphere. And that happens daily. Like I mentioned, the estimates are that it's something like 60 tons of material comes and reaches the Earth's atmosphere. I don't know what the exact number is, and I don't think we do know, but let's say about 99% of that is kind of dust size material, and that just burns up. I would think, and I think I'll be correct in saying, somewhere on Earth, a meteorite, grams or tens of grams, or maybe even a kind of kilo or so, will reach the surface of the Earth and could be found. So meteorites will definitely be falling on the Earth daily too. And then again, thankfully for us, these larger events are on the order of hundreds to thousands, tens of thousands to millions of years for those kind of very big events. So I hope that answers your question.
I hope so too. If it doesn't answer your question, or if it's given you another question, then feel free to type that in. I'll look for it. We also have a question from the grade 6 students in Mrs. Farr's class, wondering if meteorites are named, and if so, how are they named?
Yeah, so actually, in order to confirm a meteorite, they actually have to be given a name. And a lot of them are quite obscure, but in the general convention is that it's named by kind of the most local, actually kind of post office, believe it or not, or the local kind of postal address. So they're typically named after local towns and things, if they're anywhere inhabited. In vast parts of Antarctica and Africa, you'll often just see the name of a mountain range as an acronym. So for example, a famous range in Antarctica is called the Miller Range. And so that one would have, MIL, and then the year it was collected and the name of the meteorite. But a good example that is kind of close to home for those of you in southern Ontario was a few years ago, a meteorite. Actually, we detected a fireball, some colleagues here at Western, and the meteorite was found quite close to Grimsby in Ontario, so not too far from Toronto and St. Catharines. And so that is now known as the Grimsby meteorite.
Grimsby's claim to fame, I assume. A little small town. So our next question here relates to that, actually. You're talking about that fireball. And Ms. Lang's class is wondering, how hot can a meteorite get as it passes through the atmosphere?
So again, as it passes through the atmosphere, we don't know, because it's almost impossible to record to go and detect them. But we know from the fact that it will literally melt the outer surface of the rock, maybe a millimeter or two or even more, that it must be, well above about 2,000 degrees Celsius. And so if you've ever seen pictures of spacecraft re-entering the Earth's atmosphere, and you'll see kind of that nose cone that gets very hot and flames essentially coming around it, the exact same thing happens with meteorites. And so the temperatures are hot enough that they will melt the outside of rock, which, if you've ever tried to melt a rock, you probably haven't been able to, even in a campfire, because you need extreme temperatures. But it's actually one of the really interesting things that's often misconceived, is that after a meteorite comes through the atmosphere, it then will slow down enough so that it basically hits the Earth at what we call terminal velocity. So you could throw a rock off a building and it will impact the Earth at about the same velocity. So that usually means that once a meteorite lands on the surface of the Earth, it's cooled down to, so that it wouldn't be hot to touch.
That's amazing that it would take so little time.
Yeah, it's very, very quick.
So now we have a few questions about predicting and seeing that these impact events may be coming. So our grade 4s at Forest Manor Public School would like to know how much warning would be provided before an impact event.
Again, great question. The answer is it could be a lot, but it could be no warning whatsoever. And so NASA actually has a big, what it calls its kind of near-Earth asteroid survey, where they're going out there and trying to catalog all the potential asteroids and things out there that may impact the Earth. We don't have a clear view of the entire solar system around us. So, a good example is there are more telescopes in the northern hemisphere than the south. The southern hemispheres, finding objects that are coming to us from the sun are incredibly hard to detect. And so again, Sometimes we could detect things years ahead of time, but especially the small rocks, sometimes, we will have zero warning whatsoever. But it is something that scientists are really trying to draw up this catalog of what is out there and what potentially could it is in the future.
And that brings us to another question from Ms. Brankelmans, who I think may have seen a giant Hollywood movie years back and is wondering if we have a way to change the path of an asteroid or meteor that is coming towards Earth.
Yeah, so that has been the topic of some Hollywood movies in the past. It's something that, if we had to, it possibly could be done right now. But again, there is discussion going on. There are kind of conferences and there are people probably more on the military space side of things that are looking at this. There is no single good solution right now. There is the idea that you could go up and blow it up in space, which I think is what they did in some Hollywood movies. That the counter of that is that you end up with 10 smaller rocks as opposed to one big one. Is that any better? So it's something that people are working on, but we wouldn't have a solution, kind of tomorrow.
Right. And we've had a few questions coming in about the formation of meteorites. A lot of students wondering how meteorites are formed.
Yeah, and so it's actually a huge branch of science and is what a lot of my colleagues here at Western study, which is what we call this field of meteoritics. And essentially, there's maybe three kind of major categories. And so most of the meteorites that we find on Earth come from the asteroid belt or kind of around the Earth in form of near-Earth asteroids. Most of these asteroids formed as the solar system was forming, so about 4.5 billion years ago. And so these are kind of, think of them as leftover material that didn't go into forming big planets or moons like the Earth and Mars and Venus. And so those are material that have been out there since the formation of the solar system. Comets that you may be familiar with are another category of objects that we haven't really talked about. Those can also impact the Earth to form meteorite impacts. And then we came to this in answer to one of the earlier questions. Very occasionally, it's much less than 1%, 0.0001%. We do get some meteorites from Mars and some from the Moon. And that is essentially where you've had a meteorite impact on that object that has then launched a bit of it to Earth. And so those are really exciting meteorites to find because right now the only samples of Mars we have are from meteorites.
Right. So why is it important to study these impact events and the craters that they leave behind?
Yeah, so again, great question. A lot of scientists would be happy enough saying, this is something that we don't understand how they form. It's an exciting topic. The energies involved are really kind of mind-numbing, and so it's quite a challenge intellectually and scientifically to figure out just how they form. But I think there are two really kind of more tangible benefits for studying impact craters. One of them, which I think is kind of very near and dear to my heart, is this question of how did life originate on Earth, and is there life out there in the solar system? And as I hopefully alluded to in the talk, I do think, and many of us think, that impacts may have helped kickstart and maybe even being the sole responsible factor for the origin of life on Earth. And so we don't have all the answers yet, and so in studying meteorite impacts, we may learn more about life. And then, an even more tangible benefit, those of you who know Sudbury in Ontario know that it's North America's biggest mining camp. And so people have been mining Sudbury for well over 100 years now, and all the mines are there solely because of this giant impact about 2 billion years ago. And I should add that it wasn't the asteroid or the meteorite that brought the metals to Sudbury. What happened was that this giant impact event concentrated the metals so that they became economic. So there are distinct, economic benefits from some meteorite impacts too.
Right. So we are already over time here. I would like to ask one more question, and then we'll end things off today. Um, why did you choose this career path? Kind of how did you get here? And do you have any advice for students who might think this is really interesting and something they might like to pursue?
Yeah, and so I mean, so at high school and elementary school, I was always kind of interested in science. Um, I'm a geologist by background, and so for university, I went to do geology. But during my kind of first degree, my undergraduate degree, my bachelor's, I didn't know anything about meteorite impacts. Hadn't really heard about them. And then it was really towards the end of my undergraduate where I kind of first learned about impact craters and that it is part of geology and part of studying geology. And actually, it's what brought me to Canada. I got the opportunity, or I applied and I saw an opportunity, applied for it, and got that opportunity to come to Canada to do a PhD, actually working on these craters up in the Arctic. And so that really combined a passion of mine in exploration and in mountaineering and in climbing, and just exploring kind of wild places with geology, and kind of really got me into meteorite impacts. And then kind of what really keeps me involved too, I haven't really talked about it today. I've really focused on craters on Earth, but a big part of what I do is looking at craters throughout the solar system. And so that's a really exciting thing for me and for my students here at Western, I think. And I mean, advice, especially planetary science, if we think very broadly, and even just the study of meteorite impacts, you can come at it from a whole range of angles. And so, you could be a biologist and study this. You could be a chemist, a physicist, or a geologist. And so, there's lots of different ways through science to get into studying meteorite impacts or other aspects of planetary science. And then, for those interested in space in general, or if you're interested in engineering, the engineers are designing spacecraft to go out there into the solar system, to maybe bring back data so that me as a scientist can study impacts on other planets. And so there's really a whole host of backgrounds and interests that you could pursue and still end up looking at something like this. So hope that answers the question.
Well, thank you very much. That is all the time that we have today. It's been really great to learn about this topic from you, Dr. Oz, and hear about not only what we've experienced in our history on Earth, but also that it seems similar in a lot of ways across the solar system, and that we're still studying both because there's so much more to learn.
Absolutely.
Well, next week on PIR Live Event, we are discussing quantum technology and smartphone screens, and more information on this and other Partners in Research educational programs is available at pirweb.org. Thanks so much for tuning in, everyone. I hope you have a wonderful day.